class schedule for 512, I have put a few things up. I put the section 5 notes, and I put the lecture from last time. This gives you an idea of where we're going. There are 7 sections in this chapter, so next week we should finish chapter 12. And I'll be posting, the assignment for chapter 11 is due this Friday. I will be posting sometime Friday, Saturday. I'll be posting the next assignment. Are there any questions? Okay. I always have to give priority to getting lectures ready, and so I run out of time and grade dribs and drabs, but I will definitely get it by next Monday. I do still have a problem, is that one of the distance-based students still hasn't taken the exam. She was supposed to take it today. But at any rate, I'll work on that, and I'll try to get back the exams to you on Monday. If you really need to know the score, you could email me and I'll send you that. But we'll go over part of the exam on Monday. Are there any questions? Okay. So what I'm going to do, I don't think I need to come back to this, so I'm just going to open this up. I'm going to our studio. I am going to need to reference the book today. So I'm just going to bring it up here. As I mentioned to you, ebooks, I think it's here. I probably mentioned to you that I am, trying to remember how to make it bigger. Right here. Yeah. So I want to go to, I want to just show you what I'm doing. If you look at this version of the book, which is what I'm redoing, this is chapter 10. I'm kind of rearranging things, and what I have here is not how I'm going to do it. Notice in chapter 11 I put nested design. What I'm actually going to do is put the A by B and A by B by C in chapter 11, and bring the nested down design down to this chapter. What that means is there'll still be the same number of chapters, but I'm going to pull out the A by B and A by B by C into the analysis variance model. There's a certain consistency there because we talk about random and fixed effects. And so I'm just going to extend it into the 2-way and the 3-way. And so there's a natural progression under the analysis variance model. Then the other chapter is going to focus on experimental design. And as I said, there's kind of a question as to whether or not you really consider nested designs design in the sense of controlling variation. But it fits better there, I think, than up above. I mean, it could be either place. It's not as clear cut. But in terms of the length of the chapters, that might balance it out a little bit more. What we're going to be doing, again, today we're going to be covering the 3-way. But we've already covered the randomized complete block and the Latin square. And we're going to go into these 2 designs, which are also in the literature called multi-level designs, in the sense that you sort of design it at multiple levels, and you'll see what I mean by that when we get to it. They're very important designs. When I used to do back in my early years, meaning in the 70s when I was here, I basically had Phil Turk's job where I did a lot of consulting up in agriculture and forestry. And the designs, what I call the split plot and the split plot with repeated measures, were actually among the most common things that I did. It's extremely common. It's sort of like having a factorial, and then you have, and then on each experimental unit you have repeated measurements. That's extremely common design where you measure it over time, let's say. Now, there are multiple ways you can analyze it, and the methods we have here is one way. Another way is will be taught in my multivariate course. So there are multiple ways that we can approach this. Part of what you need to learn is, part of the things you need to learn is, I think that you need to learn the concepts, but the concepts don't do you very much good if you don't know how to implement it with software. On the other hand, so I'm trying to do both. On the other hand, if you just teach the software sort of mechanically and say, okay, in SAS proc this, and here's the output, and this is how you interpret it, and you don't know what's behind those models, that's not good either. So the question is, in this type of course, and that's also true in a regression course, the question is to what extent, where is that balance of teaching things conceptually but not getting into proofs about why they're true, but still teaching it using formulas and things like that. You could teach it at a lower level, and some would like that, where you sort of just give computer output and you talk about the interpretation. The problem is that gets you into trouble because you don't know the underlying ideas. At any rate, today I'm going to talk about the A by B by C factorial. And last time, just to review, we talked about the A by B factorial. And by a factorial, we mean we have two types of treatments, A and B, and each have levels. They don't have to have the same number of levels. So you could have a 3 by 4, meaning A has 3 levels, A1, A2, and A3, and B has 4 levels, B1, B2, B3, B4. That forms like a matrix that's 3 by 4. And so for the rows, you have A1, A1, A2, A3, and for the columns, you have B1, B2, B3, B4, and then you have 12 cells. And then within each cell, you have sampling. And we've been assuming that you have n observations in each cell. A couple things can happen, even if you intend to sample n in each cell. And that's kind of the ideal situation because that's a balanced experiment, and the expected mean squares work out nicely and so forth. Sometimes even if you do that, you'll get a missing value for some reason, so you don't quite have balance. Now, the expected mean squares we're going to talk about even in more depth today, they get changed a little bit if you have a few missing values or you have a slight unbalance. Then the expected mean squares that we will be computing are not exactly correct, but they're approximately correct. But if it becomes too unbalanced, then it's not only that it's not correct, it's almost impossible to compute it by hand at least. It becomes much more difficult. I mean, it's possible, it's just tedious. And it's not something that we want to do in this course. Fortunately, JMP does it for you, and I'm going to be discussing JMP today. But if you will recall, we had a model for the two-way that looked like this. I guess I can blow this up a little bit more. Actually, I can get rid of table of contents. Whoops. I can get rid of I can actually blow it up to full screen, and maybe you can see it better if I go to single page. That's not what I wanted to do. Maybe it's just better if I don't do this, and then I can make it bigger. So this is our model, alpha mu plus alpha sub I plus beta sub j plus alpha beta ij, where alpha beta ij is the interaction. That's not alpha times beta. That's sort of a symbol representing the interaction. And notice that I have k equals 1 to n in each of the cells. And so in that sense, we have balance, but I could have k equals 1 to n sub ij. In other words, I could have different number of, in the ith row jth column, I could have different number of observations than in another cell. So if we think about, this goes through, again, I do want to mention that this is the computing formula, and these are the uncorrected sum of squares, and by taking differences you can get these computations. Intuitively, the definition makes more sense, but if you were going to calculate it by hand, and if you wanted to work through one by hand, that's in the book, and the book does work through one by hand, then you can use the computational formulas on a calculator. It's much easier. I haven't been emphasizing that since it's kind of not, it's probably the only time, if you work one by hand, it's probably the only time you'll ever do it. Given the software, it just isn't something we need to do. Notice that if you look at the yijk and y bar ... the t is sort of the sum of squares of all those, and then CF is the square of this. And so you actually, if you look at this formula, you can kind of define these, and then this is sort of the I subscript represents A, so this is A minus CF. This is like B minus CF, and so forth. So you can actually kind of, by looking at the formula here, you can actually sort of see what the formula is for the computational approach. Now, last time, I worked through what the expected means. Well, I didn't work through them. These are the expected mean squares. And we're going to talk about that more today. There's a general formula. Depending on, if both A and B are fixed, you don't have those interaction terms. If A and B are both random, you have all the interaction terms. If one is fixed and one is random, you get some of the interaction terms. For the fixed one, you get an interaction, but you don't for the random one. So we have a general rule for figuring this out. And what I'm going to do is let you know, if you look at what jump does, you actually see different expected mean squares, and that means you have different types of tests. And so you might say, okay, if I run this package, I get these tests. If I run jump, I get another set of tests. What's up? Well, what's up is the difference between what I call the standard model and the alternative model. And I'm going to sort of show you the difference. And then we can look at the output so that you understand what the differences are. Basically, the alternative model puts in more interactions. And so, and I'll show you how the definition changes in just a little bit. So this was the two-way that we went through. So what I'd like to do now is go down and look at the A by B by C factorial. And so let me find out, let me look at the files, and if I go to courses at 512, notes, and I'm going to go into chapter 12, and I'm going to look at section 5. In section 5, let's look at the RMD, and I'm going to knit this. Now this is a little bit incomplete. I want to put, I'll be adding some things to this. In other words, I don't actually give the model here. I do give the expected mean squares for an example. So that's why I'm going to need to refer to the book, because there are a couple things I don't have in the notes yet. Some of these things, putting in the notes, like this table, is kind of non-trivial. It's a little bit tedious to put those kind of things in the notes. But there's at least one more table I want to put in, plus I want to put the model. There are actually two tables I'd like to put in, but one is definitely important. So what I want to do is go back and look at the model. The model's not actually, well, okay. It's split between 2 pages. What you have here is I have 3 factors, A, B, and C, let's call them. And so I have a model mu plus alpha sub I for the A factor, plus beta sub j for the B, plus gamma sub k for the C. And then I have all possible interactions. I have AB, AC, BC, and then I have ABC. Now, it's not too hard to interpret the two-way interactions. In other words, the AB, the AC, and the BC are fairly easy to interpret. It gets a little bit harder to interpret the three-way interaction. Now, in order to give you a conceptual framework of what this looks like, does everyone know what a Rubik's Cube looks like? Another little thing you try to... That's a 3 by 3 by 3 factorial. Okay, there are 3 rows, 3 columns, and the depth is 3. So those 3 3s are 9, 3 9s are 27. Those 27 cells in form a 3 by 3 by 3 factorial, and within each of those cells, I would have n sub ijk, where I represents the row, j represents the column, and k represents the depth. Okay, so think about Rubik's Cube. Of course, it doesn't have to be 3 by 3 by 3. It could be 3 by 4 by 2 or whatever. So it's like a matrix that has depth. It's like a 3-dimensional matrix. In R, we call that an array. An array can have more than, a matrix is 2-dimensional. An array can have more than 2 dimensions. And so we often, a lot of times we may work with this. For example, you may be familiar with the contingency table. So if A and B are categorical, and we have a frequency count, so we have still A1, B1, A1, A2, and A3, and B1, B2, and so forth. But if instead of measured values, we have the frequency of how many times A1 occurs with B1, how many times A1 occurs with B2, then if we have frequencies, we can actually look at independence between the 2 factors and sort of say, okay, are those 2, we can think of them as being discrete variables, are they independent of one another? And so we can analyze them as a 2-dimensional contingency table. But of course, you could have 3 factors. Now, what happens, generally speaking, when we have like 3 factors, A, B, and C, we actually model, and it might be that C is kind of an outcome factor, and A and B are predictor factors. And so we're trying to predict C, which is categorical, from A and B. Those we call log linear models, and we're going to do just, well, we won't probably get to it, but the last chapter of the book talks about logistic regression. And if, in fact, the predictor would be categorical, that would be like a 2 by 2 or a 3 by 2 or something like that. So, but generally speaking, categorical data analysis, we have a separate course, 555. It's, from my point of view, it's an extremely important course. It's a course we currently don't require in the statistics curriculum. It's a course we will be requiring in the MS curriculum soon. So not knowing categorical data analysis is not good if you get out in the job market. In biostatistics, categorical data analysis is kind of central. If you take this course and you extend it into 645, I mean, I would argue that Stat 645 is very important because it takes this course and takes it to the next level. In other words, it takes linear models beyond what we're covering. So when you cover mixed models, you go into more depth. Now it's more, it's a little bit more theoretical, but not excessively so. Categorical data analysis, arguably we should have a 600 or 700 level advanced categorical data analysis, but at this point we don't. Okay, well this is the model. So you may think this is, kind of extreme. It might be that you leave the three-way interaction out and you just say, well, I don't think it exists, I'm going to leave it out. But usually we leave it in, and then if we test for it, and if the p-value is really, really high, then we may drop it out of the model. In other words, we can drop terms out of the model. We've never really talked about dropping terms out of the model. But let's say you have the two-way, you might test the interaction. And by the way, I didn't mention this, or maybe I did, but I want to emphasize it again. If I have a two-way and I test the interaction, you may say, okay, let's suppose you test A level and it's significant, and let's suppose you test B and it's not significant, and you test AB and it is significant. Then you might say, well, can I drop B out? And the answer is no. If the main effects, even if the main effects are not significant, if the interaction is, you need to leave those main effects in. On the other hand, if I drop out the AB interaction, then I can drop out main effects. So it may be that A is the only thing that's important. B is not. So, but first I would test A. I would sort of sequentially do it. I would test the AB interaction. I'd say, okay, that's not significant. Now I fit the submodel that just has, A and B in it, in R parlance, tilde A plus B. So I start out with tilde A plus B plus A colon B in R. I test A colon B, and if it's highly, if it's not at all significant, meaning quite high, if it's marginally significant, I'd probably leave it in, like it's 0.07. I'd probably leave it in. But again, that's sort of a decision you have to make in terms of the complexity of the model. But if AB has a p-value of 0.4, the interaction, then you might drop it out, and then you say, okay, now I'm going to look at the main effects model. Because if you can say, oh, it only depends upon A, it doesn't depend on B or the interaction of A with B, that's a much simpler model. So, so you can kind of hierarchically reduce terms. So I would never delete a two-way interaction if the three-way is significant. Now, there's a problem of interpreting the three-way, but just remember that in order to drop a two-way interaction, you should drop the three-way first. And if you don't drop the three-way, you should leave all the two-ways in. And then there's some technical reasons for that. It's sort of like taking a regression model and say, can I drop out the intercept? Well, that has some pretty severe implications, because that means the regression line goes through zero. And so, you better be pretty sure about that if you do a regression through zero. Same thing here. There are reasons why you do not want to drop out two-way interactions if the three-way is significant. But the three-way is insignificant, then you can start looking at two ways, and it might be that you drop out AC, but you leave in AB and BC, or something like that. Now you get into this transitivity issue. And so you might say, well, if A and B is significant, and B and C is significant, shouldn't I really have A and C? Now, it's not transitive in the sense, if A is less than B, and B is less, in regular arithmetic, if A is less than B, and B is less than C, then it's true that A is less than C, right? That's not necessarily true here. We don't have transitivity in interactions. If AB is significant and BC is significant, it doesn't mean AC is significant. We don't have transitivity in that sense. I remember this type of argument because I recall during my PhD exam at Cornell, they actually asked me a question about transitivity relating to multiple comparisons. So that was stuck in my mind. So at any rate, these are all the terms of the model. They're what you expect. Alpha gamma is the interaction between A and C. And we just use these symbols. Now, obviously, these the A, B, and C, we can call them A, B, and C, but they're really going to have names associated. When we do an experiment here in a few minutes, we're actually going to have names associated with that. Now, if you look at this table, it's sort of a more complicated version of the two-way. And again, these uncorrected terms correspond sort of in a one-to-one correspondence. So here, for example, I have a subscript ij. I'm getting the mean in the cell ij, averaging over the third factor and the replications within the cells. And so that corresponds to AB. The subscripts ij correspond to AB. The subscripts here correspond to I. This is a continuon. That's B. The subscript, this is A. And then dot J dot dot corresponds to the B subscript, and so you have a minus B. Now notice they're minuses. And then you have a plus this correction factor, which is all dots. So again, there's a correspondence sort of one-to-one between these terms and the terms in the parentheses. But it might be interesting to sort of see the definitions for these sums of squares. But in terms of the computational formula, the only reason for having those is if you would actually do it by hand, which is not likely. It becomes even less likely for a three-way. It's certainly possible, and I think that it's worked out in the book. Of course, you have to understand that in the early days of statistics, actually statistics, goes back quite some time in probability, even before statistics. Well, statistics in terms of descriptive statistics goes back to Babylonian times, but in terms of inferential statistics, that was a lot later. Well, if we're going to test, let me first of all talk about a particular experiment, and we'll give this context, and then we'll talk about, well, how might we test the various hypotheses, and that leads into how you compute, the expected mean squares. So we're going to consider this. Stan, these notes originated from Stan Weirden, who was he was the founder of this department and a long-term faculty member, and actually just a year and a half ago passed away. But he was, he actually studied with a very famous guy at Cornell also, who was in animal science. So you notice there are a few examples from the area of animal science. But of course, this is completely, the analysis of variance is used everywhere. But here's a situation where you have bull semen, and you'd like to be able to artificially inseminate. And so that's what's routinely done now, but the question is how do you store it so that it doesn't degrade? So you archive it, and then you use it as needed. But of course, that's also true of humans now. Artificial insemination is getting fairly common, but you have to have a mechanism of storing it so that the sperm does not die. So at any rate, some of the original work in animal science went back to the 50s, and I think actually that precedes what was done with humans, and perhaps it was because you wanted to be much more careful, perhaps with humans, because you don't want birth defects to occur due to artificial insemination. So at any rate, you need to have some sort of when you have a freezing process and a thawing process, and you need an antifreeze. You need an antifreeze, and you need a buffer. And so the original one was glycerin, but later on there were many, many antifreezes you could use. And so this has three treatments. You're going to sample different bulls. So bulls is going to be one of the treatments. Now that's obviously going to be random. And then you have antifreezes, and you also have buffers. Now, when this experiment, if you look at it, there are three levels of the buffer, which are fixed effect, and I think we'll call that A. And then there are two bulls. I mean, you could have 10 bulls. You have a bunch of bulls, and you're going to sample some. Hopefully, there's not a lot of bull-to-bull variability. That would be a problem. So, estimating variance components becomes important. Because if there's too much bull-to-bull variability, that would create a problem. Particularly if the bulls would interact with the buffer and the antifreeze, that would be a real problem. Because it would be in other words, if you could only pick the buffer and antifreeze based on the particular bull, that would be a serious problem because it would make it difficult to, if you go to the next bull, the results may be different. So that would create a problem in terms of which antifreeze and which buffer you use. At any rate, now in the book, I'll stick with this. He says antifreezes are a random effect. That implies you have a bunch of antifreezes to choose from, and you select how many in this case? 3. I'd probably think that was actually a fixed effect if I were thinking about it, because I don't know. Maybe there are tons of antifreezes out there, and you can sample 3 at random. But I would probably do buffer and antifreeze as fixed and bull as random, but we'll stick with the book. That may change as I redo things. So what do we have? We have a 3 by 2 by 4 factorial, right? No, I'm sorry. We have a 3 by 2. Got ahead of myself. We have a 3 by 2 by 3. 3 buffers, 2 bulls, and 3 antifreezes. And then N is 4. N is the number of samples I get within each cell. So if I think about it, again, rows, if I represents the buffer and B represents the bull, that forms like a matrix Ij, and then K represents the depth, which is the antifreeze. So if you think about it as a if you think it as a three-dimensional object, that's 3 by 2 by 3. And then within each of those cells, I'm going to sample 4. So there's crossing. So in other words, on a given bull, the semen of that bull is used on all possible antifreezes and all possible buffers. Now you could have a different design. You actually could have different bulls. You could have a 3 by 3 factorial where you have 3 buffers and 3 antifreezes, and for each cell you have a different bull. And that would be what? That would be a two-way. That would just be a two-way but there was a little catch here. If you had a two-way, A by B, and you sample bull within each cell, then that would be like what we did in the previous section, right? Where bull was the experimental unit. But if you get semen samples and you subsample, then you have samples within bull. So you have these 2 error terms at the bottom. And that's like a nested design, except where we used to have treatment, we now have effect. In our nested design, we had treatment, then we had experimental unit within treatment, and then we had sample within experimental unit. Here, if we did it this way, we would have a factorial, a 2-way factorial. We sample bulls in it, and then we have subsampling within each bull. Same kind of concept, except where we had one treatment, we now substitute a factorial. You can always do that. And in fact, the error term in all cases will be bull. If we have fixed effects for A and B, if A and B are both fixed, then we use the bull effect to test everything. Now we could look at bull-to-bull variability in that case by subsampling. We because we can get a variance component for the bull-to-bull variability. But that's not the way we're doing it. We're assuming everything is crossed. Okay, each bull, all antifreezes and all buffers are tried on each bull. You see the difference between that and nesting? In nesting, I would have, for a given antifreeze, I have different bulls for each level of antifreeze and buffer. That would be a completely randomized design where the treatment is actually a factorial. So you need to sort of think, that's why I say you need to think differently about what's the treatment design, and then you also think sort of more generally, well, what is the experimental design? That's kind of another reason that I really should put nested below the factorial, because once you talk about a factorial design, whether it's just a one-way or a two-way or a three-way, any place you have treatment, you can actually substitute that in. And you'll see that when we get in sections 6 and 7, we can extend those ideas to more ideas. At any rate, this is the data. So if you were computing by hand, you have to get all these types of totals. So the actual data is in this sort of center part here for A, B1, and C1, C2, and C3. Here's the data, and then here's the data for A2, and then here's the data for A3, and the data for B1 now with A1, B1 with A2. And so at any rate, this gives you all the data in sort of a tabular way. Of course, that's not what the data is going to look like when you run Aura. Did I give, yeah, what I did is I said read.table, which reads in a text file that's in tabular form. But in this case, we have buffer, we have 3 columns for each of the 3 predictors, and then viability is the response variable. So we have A1, A2, and A3 for the buffers, B1 and B2 for the bull, and if you printed out the whole file, so I will maybe do that. So if I read, am I in the right spot? Yeah. I may set this to working directory. So if I read in the file, which I've named Seaman, and if I look at this first 6, but actually if I look at everything, this is what it looks like in a tabular form. Now notice we're sort of repeating everything because we have to get all possible combinations, and you notice how many observations are there? There are 72. So we have a 3 by 2 by 3, right? So that's 6. 3 by 2 is 6, and then by 3 is 18. And now there are 4 observations in each cell, so if I multiply 18 by 4, that's 72. So we stretched the data out, but we've had to specify and repeat lots of A1s, A2s, and A3s, and so forth. Is everyone clear how this is what the original data looked like, and we just read it in the R, and it looks basically the same as the original text file. If I attach this, then I can fit. Oh, by the way, this asterisk sign. If I put a plus there, it would only fit the main effects. If I say buffer plus bull plus antifreeze, it would only fit the main effects. By putting an asterisk, it expands it out to a factorial. It's a shorthand way of doing it, so you don't have to say buffer plus bull plus buffer colon bull plus antifreeze plus buffer colon and so forth. In other words, you could write it out if you want, but if you're writing a complete factorial, then this is quicker. So, we can fit this, and then we could look at an analysis of variance table, and that's the analysis of variance. Now, the problem is that everything is being tested by the residual, and since we have random effects, this is not right. Okay? So, so in order to find out what tests what, we have to get the expected mean squares. So let me just sort of show you what those expected mean squares are. So that column under expected mean squares, notice that for ABC, you have sigma squared as the residual variability. And then for the A by B by C, you have sigma squared plus 4. And so you might ask, well, where do I get the 4? And then you have sigma squared ABC. And then for BC, I have sigma squared plus 12 times sigma squared BC, and so forth. Now notice, up for buffer, I have a sum of the alpha sub I squares. And so, in this particular case, that's because it's fixed. And the others are sigmas because they're random. Now let me mention that anytime I have something random, like if B and C are random, then any interaction involving BC is also random. So A by B has a fixed effect and a random effect. Because something in it is random, that means it is random. So notice that I have a sigma squared AB. I don't have a sum of the alpha betas. That's because the B is random in this particular example. So there are the expected mean squares. And if you would go in and run in this in jump, you would find it's a bit different. Well, I have a few more terms in jump. And so you might ask, well, why is jump different than this? It's because jump uses the alternate model, and this is using the standard model. So, if you have your book, if I can find it here, it's up here. This table is going to be the guide about how to compute expected mean squares. And there are a couple rules. The rules are given. Where are the rules? I thought they were there. Oh, they're below. Okay. So they're on the same page, but I can't see the whole page. But notice I have a fixed term and a random term. And so basically, I'm going to have a term in my model, and it's either going to be the top or the bottom, depending upon whether it's fixed or random. Now, the theta squared sub A is simply the theta squared sub A right here. That part is just a shortcut for the sum of the alpha sub I squared over A minus 1. It's just a shortcut. Okay? Theta squared sub B is just the sum of the beta sub j squared of b's over b minus 1, and so forth. Theta squared sub AB is the sum over I and j of alpha beta squared over ij divided by a minus 1 and b minus 1. Oh, I should have emphasized that those denominators are the degrees of freedom, but I should emphasize that the degrees of freedom are actually quite easy to compute. And you know, so for example, for A, there are A minus 1 degrees of freedom. For B, there are B minus 1, and for C, there are C minus 1. But what about AB? Well, it's just the product of A minus 1 times B minus 1. And AC is A minus 1 times C minus 1, and so forth. A by B is simply A minus 1 times B minus 1 times C minus 1. And then the error is simply, you also have 1 for the intercept. So if I'd add all those up, and how many total observations do I have? For the balance case, I have A times B times C times N. That's how I got to 72, right? In that particular example, I had 72, because I had 3 times 2 times 3 times 4. So there were 72 observations. And so in that particular case, A would have what? 2 degrees of freedom, right? B would have 1. C would have 2. AB would have 2. AC would have 4, and so forth. So if I add all those up and subtract them from 72 and subtract 1 more for the intercept, then I get the residual degrees of freedom, which actually turns out to be just A times B times C times N minus A times B times C. You can algebraically work it out if you want. Okay. So, now you might notice that there's some advantage to being able to test by the error term because it typically has a lot more degrees of freedom. In other words, the AB and the BC only have 2 degrees of freedom. So if I have to use those for my error term, I don't have very many degrees of freedom. Even A times C is 4 degrees of freedom. So the problem is that when we compute some of these, there's kind of a strategy here. In terms of random and fixed effects, and this really also depends upon the standard of the alternative model, because the alternative model puts in more terms into those expected. It doesn't have less, it has more. Certain terms drop out for the standard models that don't drop out for the alternative model. And I'll show you exactly where they are. And if you look at the output here versus the jump of the same Seaman data set, you'll see that it's more complicated for the alternative model than it is for the standard model. I'm not saying which one is correct. As I said, the standard model does a finite correction sampling, whereas the alternative model does not. So from my point of view, the assumptions for the alternative model are stronger. Okay. So going back to this. So let's read the rules. It says sigma squared is found in every expected mean squared. The coefficient for any sigma squared or theta squared will contain N, A, B, and C if these letters are also not found in the subscript of sigma squared or theta squared or sigma squared or theta squared. Let's just take a look at this particular rule. This is the coefficient, so let's take a look at the coefficient. So for example, here I have A, okay? I have A, and so I have N, and then let's look at ABC, for example. So I'm not going to have A as part of the product. I actually have everything but A. I have N, B, and C, but notice I don't have N times B times C. So ABC, I have just the N plus some function of B and some function of C. Now those functions are actually 0 or 1 functions. I either multiply by 0 or multiply by 1. And whether they're 0 or 1 depends upon whether it depends on a couple of factors. I'll come back to that in a minute. But if I look at AC, notice AC, it doesn't have, when I'm looking at A, it doesn't have N or B. In other words, AC doesn't have B, so it does appear below. And it also, I'm always going to have, I'm going to have that N also in all cases. Now notice there's nothing. In other words, if I'm looking at A, there's nothing for BC, and that's because A is not in BC. So that term is not going to appear, nor is C or B by itself. So when I'm looking at A, if I'm looking at A, the BC stuff involving just B or C or BC will not appear. But anything including A will appear, or it may appear. Let me put it that way. It may appear. So ABC will appear, AC will appear, AB will appear, and A will appear. The subscripts are what's not in the above. In other words, forgetting the F's a minute, it's what's not above, but you don't include A. So if you have AB, in other words, NC is not included. But there is something in B. If I'm looking at A, there's an f of B. And the question is how do I compute it? So you have to kind of study that and look at a few of them. For example, let's look at the mean square for B. Let's look at the second row, and let's look at the column corresponding to BC. Okay. Now I have a B. So what are the coefficients? It's going to be n times A. Okay, B won't appear. Even though B appears above, it won't appear because I'm looking at the mean square for B, and I don't include any coefficient in the row that corresponds to the mean square. I do not include in that coefficient. So I don't have an NBA. I just have NA because B appears as a subscript for the row I'm looking at for the mean square. But what about C? Well, it sort of appears. In other words, C is above. C is above, and it's going to appear as an F, and it's not a B. So it appears above, but it's not a B. So it's going to appear as an FC. Okay. So it's a little bit complicated. There are actually only a couple of rules, but it's a little tricky. You have to kind of study it a little bit. So at any rate, the coefficients for the interaction will also contain the FA, FB, or FC if the letter is found in the subscript of the sigma squared of this, but not in the subscript of MS. So if it's found in the subscript of the column, the top of the column, but not in the row, then it appears as an F. Okay? And so what are these F's? The coefficient of FA equals 1 if A is fixed, and FA is 0 if A is fixed, and it's 1 if A is random. Now that is the standard model. How does it differ from the alternative model? In both cases, they're 1. In other words, whether it's fixed or random, it's 1. So in effect, all of those F's become 1 in the alternative model, but some of them drop out for the standard model. Okay? So, again, this is sort of the general rule, and, you know, it becomes a little bit tricky when you look at it. So for the Seaman example, I have a 4 because that's n, and so for A, and the n's going to be everywhere, so it's going to be 4 times something. Now in the next one I have 8. Now remember, in this particular case, that A is going to be fixed. I have a sum of the alpha sub I squares. A is going to be fixed. Okay? So in other words, you could ask the question, do I have an interaction with AC? Yes, I have an interaction AC. Why? Because C is random. I have an interaction with AB because B is random. So in other words, I'm getting, and I have an interaction with ABC. Why? Because B and C are both random. So those are all going to be there. But now let's look at B for a minute. Let's look at B. Now, B is random, but A is fixed, and C is random. So B. So what does B interact with? Does it interact with AB? No, because A is fixed. Does it interact with ABC? No, because A is fixed. Unfortunately, for the alternative model, they're there. So if you look at this jump, and we will look at it, you're going to find it. And again, so the 8, if I have 8, so take the 8 for the sigma squared AC. What's missing? Well, the B is missing, and also N is missing. N is already there, so it's 4 times something. How did I get 8? Well, B is 2, so it's 4 times 2. B is missing from that subscript, right? So if it's missing from the subscript, it's out front. Think of it that way. And so what about AB? Well, what's missing from the subscript? C. So what is C? Well, it's 3. So 4 times 3 is 12. So it's not as hard as it may have seemed. We kind of look at it and say, okay, for the standard model, you know, I'm going to not put in an interaction if I'm interacting with something fixed. So let's go down and look at B a minute. As I said, because A is fixed, and I'm looking at B, there's no AB, right? There's no ABC. Well, first of all, there's no ABC, and there's also no AB. And there is no AC because B is not there. So it's also gone. And that's gone from both models. And again, if I look at the subscripts, if I say BC, well, what's missing? Well, A is missing, which is 3 times N is 4, that's 12. And if I look at B, I say, well, what's missing? Well, what's missing is A and C. So I have 3 times 3 is 9, and 4 9s are 36, which is N. So, so these rules seem a lot. If you just look at the rules, they seem a lot of arcane. But actually, once you do this, you can kind of write them down pretty fast. Now, of course, if it's not balanced, you don't have these nice little numbers like 4 and 3, and these numbers don't work out so nicely in that particular case. But again, this will be approximately true as long as we almost have balance. So what do I mean by almost? Well, I may have 1 or 2 less in a few cells, 1 or 2 more, but if basically the n sub I, j, k's are all about equal, then you can probably use this as a guide for doing testing. Now, JUMP actually will work it out. So now there is a way to do this in R, and this is something that there is a way to do this in R, and I haven't introduced this concept. SAS has this concept of type 1, type 2, and type 3. It actually has type 1, type 2, type 3, and type 4 sum of squares. And in R, if you wanted to get the correct test, you have to use what's called a reduction notation. And the reduction notation would, suppose I wanted, well, even then you have to be careful because of fixing random effects. But if everything were fixed, there's no problem as long as it's balanced. But even if it's fixed and it's unbalanced, you still have a problem. If it's fixed and it's unbalanced and mixed, you have a bigger problem. If the case is completely fixed design, where all the factors are fixed, but they're unbalanced, you can easily solve this problem using R. If it's mixed, trying to do it this traditional way, and I'm going to show you what happens in JUMP, is not so trivial. But I'm going to show you in JUMP how you would do it in R. What R, and this is sort of a philosophical thing, because the main sort of leader of the R camp basically doesn't believe in the so-called traditional way of doing it. And so therefore he didn't implement the traditional way in the main functions that he used for mixed models in R. I'll show you, I can show you in JUMP exactly the differences in philosophy. Okay. At any rate, do you have some notion about how you compute the coefficients? You need to study the rules and then come back and say, okay, can I reproduce those? Yeah.
I think there's one coefficient that is different from other calculations, the MSAC, 8.
There may, I think there is one wrong. Which one is it?
Yeah, 8 of sigma A squared.
In which row?
the 1, 2, 3, 4, 5, fifth row.
The AC?
Last term. Yeah.
AC, and then I go across the what?
8 sigma squared. The last term.
Oh, the sigma, the last term.
They should be
Sigma
24.
squared sub A. Yeah, you need B times C times N.
4 times 2 times.
Yeah, that's right. Yeah. Thanks. I think I had found this before, but I had forgotten. Okay. So you might want to mark that in your book that it's incorrect. Otherwise, you'll pull your hair out. So you should take a look at that, and each one of these, it's fairly easy. Like this is C times N, so this is 3 times 4, and they're pretty easy once you get the hang of it. So like with ABC, you're not going to have, well, you also have to do the zeros and ones. If you have AB, which is fixed, it's not going to, you're going to have an ABC in that case, but because C is random. Okay. Now, as I said, the only difference between, why do I have so much trouble? Oh, here it is. The only difference between the standard model and the alternative model is for the alternative model, f of A equals 1 if A is fixed, and f of A. In other words, they're always 1. Whether it's fixed or random, they're 1. And that just means you get more terms. You get more terms. So if you look here, if you looked here, and A, B, and C are R's, so if A is fixed, let's say A is fixed, if A is fixed, anything with an FA would be 0, right? So let's take a look at the B term. The B term right here, f of A, since A is fixed, would be 0. That would be 0 for the standard model and 1 for the alternative model, which means the coefficient for ABC would be there and so forth. Okay, so let's so notice that it's not there here, but you'll see in JUMP that it is there. So let me just quickly probably not going to have time to do this. When I ran this, what I did is I had some R code. This is actually a table right here, and the headers are here, and the names for the rows are here. So I took the third column and I pulled out the third column. I have a comma 3. I pulled out the third column, okay, and I named them, and so that third column right here is actually the mean squares. And then what I did, embedded within the code, if you look at the actual code, I actually computed the correct things. Now notice, in order to get the test for A, and let's go back and look at A a minute. What I'm claiming is the denominator, in order to get things to cancel out, I have to take AC plus AB minus ABC. Let's see why this works. So if I look at A, where is that? Oh, it's in the book. So if I look at A, I don't have anything that looks like these first 4 terms. I can't pick a mean square that actually has those first 4, right? But if I take AB, let's see, what is it? AC plus AB minus ABC. So if I take this one and add it to this one and subtract this one, So this would be a 4 plus a 4 minus a 4. That gives me this. And then this term gives me, this term for AB gives me this one. This term for AC gives me this one. So if I take the AB, take this one, if I divide the mean square for A over the mean square for AB plus AC minus ABC, I get the correct stuff that cancels this out and to test this. Do you follow what I'm saying? Now the problem is, what do I use for the degrees of freedom? Well, the degrees of freedom for the numerator is A minus 1, but what do I use now? This is called a synthetic F test. I have to construct the denominator to match so it cancels out everything except the one term I'm interested in. But then how do I compute the degrees of freedom? Well, they're a little bit tough to compute, and I'm going to show you how that's done in JUMP. I'm not going to have time, unfortunately, today to show you the JUMP. But so we construct, what I did is I didn't actually give a test here, but I'll show you how it's done in JUMP. And these tests are all okay. It's this one that's a problem. So I had to do a synthetic test here. So I have the numerator mean square divided by the denominator mean square synthesis. Now the only one that's a problem is the A effect. But in JUMP, there are more problems for the alternative model. I think there are probably 3 of them you have to do a synthetic denominator, because it has more of those interaction terms in. So you can't get a corresponding test for it. But these are the actual F values, though, using this model. And so what's significant here? Notice that antifreeze is significant. The Bowl effect is not, although it's 0.1. It's not way off. There is some variability due to Bowl, but it's not way off. The antifreeze, in fact, is, it is significant. And the interaction of buffer with antifreeze is significant. Unfortunately, the well, actually, do I have it right? I'm trying to look at it. Buffer by antifreeze is significant, right? Now, but fortunately, if I'm looking at the last column with the p-values, okay? So fortunately, there are no Bowl effects. In other words, the Bowl does not interact with the buffer or the antifreeze, and the 3-way is not significant. So, and in fact, the antifreeze with the Bowl by antifreeze and the Bowl by buffer by antifreeze are not even close to being significant. So technically, you could think about deleting some terms from the model, but you don't do them all at once. You might say, okay, I'm going to drop the 3-way interaction out. What happens when you drop it out? It goes into residual, and therefore the degrees of freedom as residual is greater. But you want to make sure that that's called pooling. I'm pooling the 3-way interaction with the residual, and so the degrees of freedom now will be 58. Now, if I would take that 3-way, which has 4 degrees of freedom, and put it down in the residual, it would have 4. But the 2 sums of squares would get added together. The 2 sums of squares would get added together, and then the mean square would divide by 58. So you want to make sure that if you pool, it suddenly doesn't blow up. Even if it's not significant, it could make that pooled error term bigger. So that's why you have to be cautious about dropping things out, because if it's bigger, it's harder. It lowers your power in a sense, because it's harder. It's the denominator, so it drives down. If it's bigger, it makes, when I divide it in the numerator, it's going to be smaller. Now you have more degrees of freedom, so it's this kind of trade-off thing. But so you have to be careful. Well, I'm going to stop here. I just want to show you. If you bear with me just 1 second. Well, I'll just start. What I'm going to do next time, I was hoping to finish this today, but I'm going to show you how we do this in JUMP, and we'll compare the 2 models between R and JUMP. In JUMP, as I said, it uses the alternative model, and you can also easily get the variance components and so forth.